Good morning, everybody. Hope you had a good weekend. Whoever started this video, I am going to ask you to pause the video on occasion, so if you are not already sitting up by the laptop, if you would, please. First thing I'm going to say is if you have not already, take a few minutes and compare your answers from your table derivatives. I know probably most of you got that done on Friday, and so maybe you're already satisfied with your answers. But if not, go ahead and pause the video for a minute, compare your answers, make sure you guys are all on the same page. Okay, once you've been able to check those answers, let's start talking about today's lesson. Today's lesson goes by a couple of names. Local linearization, linear approximation is what I'll call it a lot. And it's something that we've already done, and in fact we've already done it quite a bit, and it's just finding equations of tangent lines. It's really all it is, but we're going to talk a little bit more in context as to why it's done the way that it is. So tangent lines, so far we've been doing them because the calculus requires us to find the slope of the function at that point, right? We have to find a derivative to figure out what m is. And so I've got this formula here that I introduced the other day. And the other day I called it y. Here it's referred to as L of x. And that's not uncommon that we will call a linear approximation L of x. But the formula is just the formula for a tangent line, exactly the way that we have done tangent lines in the past, and exactly the way we did them just the other day. Okay, so the process does not change. But what we're going to talk about right now is another way that these get used. So tangent lines, the deal with tangent lines is that we use them to approximate more complicated functions, right? This function here in this picture, this curvy function, its behavior might be hard to calculate. But maybe we have some data, and so we're able to actually find out what's going on at one specific point. We're able to get a slope, we're able to get an x and a y, and we know what's going on right here. Maybe we don't really know what the rest of this function looks like, but we know what's going on right here. Well, the idea behind linear approximation is that if I were to zoom in really, really close onto this thing, while I don't necessarily know what's going on anywhere else in the function, if I were to choose some other x that's really, really close to the x that I did my tangent line at, and plug a value into my tangent line, right, and it would give me this point right here, well, I know that this is not a point on my original curve, right, because I'm plugging into my tangent line. So I know my answer is not right, but it is really, really close to being right. Right? It's just a little bit a ways away from whatever my actual function is. And so the idea behind tangent lines is that as long as the point that we are choosing to plug in is very close to where our point of tangency is, then we should be able to get an answer that, while not accurate, is actually quite close to what our original function is doing. So that's what we're going to do today, is we're going to find tangent lines, and then we're going to plug in something close to that point into the tangent line to approximate what f is actually doing. Okay, consider this problem. Directions are: find a local linearization to f at a. That means find a tangent line. Right there is what that means. Use L of x, which is your local linearization, L of x represents your tangent line, to approximate f of a plus 1. What does that mean? It means I'm going to do a tangent line at 0, and then once I have my tangent line, since a is 0, 0 plus 1 is 1, I'm going to plug 1 into it and see how close it gets to what this thing is actually doing. All right, so recall that our equation of our tangent line, I'm going to use the one we saw on the page before. That is going to be f of 0 plus f prime of 0 times x minus 0. Right? That's just using the formula we've been looking at, but I plugged zeros in for the a's, right? All right, so what I want you to do is I want you to find f of 0 and f prime of 0. Pause the video for just a minute while everybody can do that math. Once everybody's got f of 0 and f prime of 0, come back. Okay, let's see how we did. F of 0 is square root of 4 minus 0 or 2. F prime of 0, over here I've got f prime of x. Right, it's a chain rule derivative, right? So it's 1 over 2 square root of 4 minus x, because what's in the radical stays the same, times the derivative of what's inside. The derivative of negative x is negative 1. Okay? Plugging 0 into this, I get negative 1 over 2 square root of 4 minus 0, which is negative 1/4. All right? Okay, if we're good with that, go ahead and pause the video again and create your tangent line. All right, so our tangent line is 2 minus 1/4 quantity x minus 0. If you don't have that minus 0, that's fine. Normally there will be something other than a 0 here, but since this was a 0, you could just have negative 1/4 x. But this is our local linearization, our linear approximation. All right, so now we're going to do this part of plugging in f of a plus 1. So in our case, a is 0. 0 plus 1 is 1. We're going to plug 1 into this. Now, our function is called L of x, and so we write L of 1. That is equal to 2 minus 1/4 times 1 minus 0. All right, so that's 2 minus 1/4, which is 7/4. Now, the whole goal of doing this is not so much to find L of 1, but instead to get an approximation of f of 1. And so what we do is we say that f of 1 is approximately 7/4. Right? It is important to have the approximation here. All right, everybody clear on that? L of x is equal to this expression, so L of 1 is equal to 7/4, but L of 1 is simply an approximation of f of 1. So f of 1 is not equal to 7/4, it's just close to 7/4. Okay? To give this a little more perspective, let's think about what f of 1 would actually be. All right, f of 1 would actually be the square root of 4 minus 1, which is the square root of 3. Well, if you plug that into your calculator, I think you'll get something along the lines of 1.732. Well, 7/4 is 1.75. Right? So it's not bad. We're not even picking a number that's that close to where we did our approximation at. Right? The actual function gives me 1.732. My approximation gave me 1.75. And the whole idea is it's tough to know what the square root of 3 is, right? That may be tough to come up with, but I can do a tangent line and do that math in my head and get an answer that is very, very close to the true answer. So that's the purpose of linear approximations. So here's an example of something that you'll have to do in your homework, and it's just a clever use of this same idea. Let's say that I wanted to know what the cube root of 9 is. Well, I'm going to do a local linearization, and so that means I need a couple of things. I need to determine what my f of x is going to be, and I need to figure out what my a is going to be. Well, it's not too hard to see that I want my f of x to be the cube root of x, right? Because I'm trying to mimic that function. But what's not obvious is what my a is going to be. A common mistake is people think you want your a to be 9, but I don't want that because I don't know what the cube root of 9 is. I want to choose a value that is close to 9 that I do know the cube root of. And so that number is 8, because I know the cube root of 8. All right, so now take a minute, pause the video, and figure out what this local linearization is going to be if your function is cube root of x and your a is 8. Before you get too far, I should point out also that you're going to need to know how to raise a number to a rational exponent. And so like if I wanted to evaluate 4 to the 3/2, that is power over root, right? I'm cubing the number and I'm taking the square root. And so my advice to you is to always do the root first. So in this example, I would take the square root of 4, that's 2, right? And I still have to cube that number, and then 2 cubed is 8. So 4 to the 3/2 power is 8, because the square root of 4 is 2, and then 2 cubed is 8. This 27, you're going to work the same way. I'm going to take the cube root of 27 first, which is 3, but I still have to square that number, and 3 squared, of course, is 9. The reason you want to take the root first, you don't have to, it works either way, but in the case of 27, if you were to square 27 first, that's a problem without a calculator. So it's a lot easier to take the cube root first, make the number small, and then raise it to whatever power you need to. Go ahead and pause that video now and do the problem, please. Okay, so if you did your linear approximation correct, you should have 2 plus 1/12 quantity x minus 8 as your L of x. And now we're going to actually do what we set out to do, which is now to plug 9 in for x and get an approximation. All right? So when we do that, we get that L of 9 is equal to 2 plus 1/12 times 9 minus 8, which is simply 2 plus 1/12, or what could we call that, 25 over 12, 2 and a 12th, whatever you want to call it. Plug that into your calculator, get yourself a decimal, then plug the cube root of 9 into your calculator and compare them. And I think you'll find that they are pretty close. All right, so your homework comes from the back page of that related rates packet that you had on Friday. And I want you to do 1 through 9 odds on the linear approximation page. That homework will be due tomorrow. Thanks a lot. Hope you guys have a good day.